Hello again, everybody. This is the second talk by Jaqueline Noronha-Hostler on neutron stars. For us, just a very brief introduction for her. She's got her PhD in Frankfurt, as I already said last time around, has been to postdocs at Columbia and Houston, faculty position at Rutgers, and is now in a faculty position in Urbana-Champaign. She's been doing neutron stars in all manner of ways during her career, and now I guess we're getting to research that she's been doing by her own, going beyond the introduction that we saw last time. All right, take it away.
All right, thank you very much for having me, and I'll be talking about cracking open neutron stars today. So what you can see here are two neutron stars that are orbiting around each other. This is called the in-spiral right before they touch. At the point that they hit each other, this is the post-merger. And that can be described by relativistic fluid dynamics coupled to general relativity. And so this is an example from GW 170817, where not only could they get signals from the gravitational waves, but the key part is that you had an observational signal. And so you could actually see that there was light afterwards. And that was really important. So you knew that was neutron star merging and not just black holes merging. And so that was very, very crucial in terms of understanding that we could actually observe neutron stars merging. So why do I like neutron stars and neutron star mergers specifically? Well, what I find very cool about them is they really combine the four fundamental forces of nature. You have electromagnetism, you have gravity, you have the strong force, and you have the weak force that all come together for them. And so the question is then, how do we observe these things? What are the different stages that happen in a merger, and what can we understand from them? And so up top, you can see the signal actually from a gravitational wave event. And in this very early part, what you have is this is the in-spiral, where the neutron stars are not yet touching at this point. We can consider them cold, although our reference is for cold depends on our degrees of freedom inside. So since we're talking about protons and neutrons, our reference for cold is actually very, very hot for most other people. It's 10 to the 6 Kelvin. But if you then think of those on scales that are relevant for the interior of a neutron star, it's actually 10 to the minus 8 or 10 to the minus 5 MeV. So it's much, much smaller. This is effectively zero in my mind. And so in this in-spiral phase, what happens is that the two neutron stars, they feel the gravitational pull from each other and they start to squish. And this squishiness depends on the internal pressure of the neutron stars. At some point, they get closer and closer until they actually touch each other, which is called the post-merger. This is, as I just said before, can be described by numerical relativity, or essentially general relativity that's coupled to relativistic fluid dynamics. And that point is extremely hot. This is when you're colliding things, you've produced enormous amount of heat, and it gets up to 10 to the 12th or Kelvin, or in the units I'm used to is 100 MeV. And so these are very, very hot temperatures, and temperature definitely plays a large role in this stage. And the last stage of the merger is the remnant. This is what is the end state, what happens afterwards. You could have a really heavy neutron star. You could have a hypermassive neutron star that is stable for a little while, but eventually collapses to a black hole. Or you could have something that directly collapses to a black hole. So all of these different scenarios depend on the masses of these initial neutron stars that are merging with each other. Now, in terms of what we actually have data for today, that is only from the in-spiral phase. We don't actually have data from the post-merger. The reason for that is it's really an issue of the signal-to-noise ratio. There's just too much noise right now to distinguish what is the signal from the post-merger phase. And for the remnant, that's a bit harder to say. From GW 170817, they couldn't see anything after the merger. It could be that it went directly to a black hole, but it's a bit hard to say. So what happens when we actually crack open a neutron star? The part that I'm very interested in is this very interior here, to see if we have something like quarks inside the neutron star. So if we take out a slice of a neutron star, we can look at the different slices, the different radii. And as you go from the very edges, the crust, it's less dense. And if we go into the interior out here or in here, it's much, much more dense. And so these very outer crusts, essentially a combination of nuclei and a degenerate gas of electrons. This is very similar to what goes into a white dwarf even. Now, eventually, if you continue squeezing matter as you go deeper into the star, you add more and more neutrons to these nuclei. And at some point, it actually becomes hard to add another neutron and it drips out. It's no longer stable within that nucleus. And so this is the point called the neutron drip line, where you have then a combination of nuclei and free neutrons. Now, if you continue to squeeze matter further, you no longer have stable nuclei, but instead these neutrons essentially form in weird shapes that are called pasta phases because they look like various types of pasta. Now, at some point, you can even go beyond that, where you no longer can even form these structures, but rather what really matters are n-body correlations. That could be like two protons or two neutrons or a proton-neutron interacting with each other, or three-body interactions. Essentially, the deeper you go into the star, the more body interactions would play a role. Now, at some point, we have to go even beyond that. And that's when all these question marks show up. We don't actually know what is in the interior of a neutron star. We have a lot of ideas. You could have something like hyperons. So those would be strange baryons that are actually stable, whereas in the rest of the universe, they are not stable. You might even have something like quarks that could be inside the core of a neutron star. And so these are, in fact, the questions that I am trying to think about quite a bit these days. So to give you an idea of the scales, the most relevant, not the only relevant for sure, contribution at least to the pressure of a neutron star has to come from quantum chromodynamics. And so this is essentially, if we think about atom, you would take the nucleus, which on the atom is around 10 to the minus 10 meters. A nucleus is certainly much smaller, 10 to the minus 14 meters. And if you get then to a single nucleon, like proton is, for instance, around 10 to the minus 15 meters. And if you want to unlock what's inside a proton, you would get quarks and gluons, which their interactions are on the scale of around 10 to the minus 19 meters. So very, very, very tiny scales. And I like to compare that in terms of order of magnitude also to a gravitational wave event, for instance, GW 190814, which I'll be talking about later on. And that's around 10 to 22 meters away from here. So in terms of order of magnitude, understanding what's going on with quarks is about just as difficult as what's going on with some of these gravitational wave events. They're almost about the same distance away in terms of order of magnitude from like the scales of a human. And now this GW 190814 is very interesting because you can see here on the top half, you have a neutron star, on the bottom half, you have a black hole. And so I'll get into that more later on, some of the mysteries around that. But to back up a little bit for the standard model, is what I'm interested in really is the quark part of this. And so for neutron stars, quark interactions are what are really relevant. If you go to other parts of the phase diagram, you would start thinking about gluons and other contributions as well. But in terms of the quarks, in fact, what we're really concerned about is the light quarks, which are the up and down quarks, and potentially the strange quark as well. Things like charm or top or bottom. They're so massive that in terms of which baryon density they would appear at is way beyond probably the central density of a neutron star. So what happens with quarks and gluons? So I said already that we see quarks inside a proton, and that's because essentially quarks and gluons are always confined within a bound state. And so a proton is here, for instance, you have two up and a down quark. You can get antimatter as well, so that would be all antiquarks here. You could get a neutron that's up, down, down, or a lambda, that's when you actually have a strange baryon. So I mentioned hyperons. So a hyperon is something that has a strange baryon or strange quark inside of it. And then you can get other things that are mesons. Those are not quite as relevant for neutron stars, but that's when you have a quark-antiquark pair. And you can, of course, get ones with strangeness in them as well, or even something like a JSI, that's a charm-anti-charm pair. So anyways, in everyday life, in this atmosphere here, we don't have free quarks just wandering around, rather they're always stuck within hadrons. And so I'll talk about the influence of both of these different types of hadrons, as well as how is that different when the quarks are your main degrees of freedom and they're no longer bound within a hadron. Now, what typically happens if I had some sort of particle? Imagine I had a quark antiquark pair like a rho meson, and I wanted to pull that apart. Essentially, what would happen is that would be like one of these finger traps that you might have played with as a kid, where you pull it apart, and the farther you try and pull them apart, the stronger the force between them. And it gets to the point where it's actually easier to create a quark antiquark pair from the vacuum than pull these individual quarks apart. So this is the idea of confinement. And so what actually confines these things is it's really the gluon interactions between the quarks. They are what mediating these interactions between quarks. And so I tell my kids this is the stickiest glue in nature, which is kind of exhibited right here. So then the question is, everything that I'm talking about here that is relevant for the neutron star is coming directly from QCD. So why don't I just go solve? I can write down the Lagrangian right now. I have gluon interactions, I have quark interactions, I have interactions between quarks and gluons. Why don't I just solve QCD? And the issue is essentially, I can't, at least not in the regime that I'm interested for neutron stars. We can solve QCD at basically vanishing baryon densities, and maybe we can perturb slightly around that regime. But when we talk about neutron stars, this is at zero temperature and very, very large baryon densities. And there's just no way in my lifetime as a physicist that I'm probably going to see any results in that regime directly calculated from QCD. Now, there might be some hope someday from quantum computing, but again, this is way, way, way far down in the future. So what do I do instead? Well, what I'm interested in is understanding the equation of state. And so I'll talk in a little bit more about the details of that. But what's interesting is that what goes into the equation of state are the degrees of freedom, these very, very tiny scales. And somehow how these quarks and gluons interact, or even how the hadrons interact, is then influencing what the mass and a radius is of a neutron star that's hundreds of millions of light years away. And so to me, that's just amazing that these tiny degrees of freedom can influence something that we can see from so far away. So understand a little bit, and for those of you that saw my talk last week, this is a bit of a review, but I think it's just important to remind ourselves, how do we actually understand what the mass and radius of a neutron star are? Is we can use structure equations. And so if I have my neutron star right here, I can pull out a tiny fluid element, and essentially on the top and the bottom of that fluid element, I have pressure, right? And so pressure, if we go back to physics 101, is just force over area. And from there, we can understand that the force of gravity is really what is playing a large role here. And so what happens inside a neutron star is that you have the force of gravity pulling you in, and the force essentially coming from pressure, pushing you outwards. And that pressure has something to do with your degrees of freedom inside the star. And then the other thing that you solve is the mass equation, where essentially you just take your density, and you assume that you have a spherical object, and you can integrate outwards and figure out your total mass. And so the way you solve essentially these two coupled differential equations is you pick some sort of central density and you integrate outwards until you get your pressure to go to zero. And that's actually the surface of your star. Now, in reality, of course, we need general relativity. And so these are the Tolman-Oppenheimer-Volkoff equations, or TOV equations. And what you need to really close these equations is you have a question in terms of what's the mass and radius. That's the outcome that you want. But you also need to then have relationship between your pressure and your energy density. You can write this in terms of mass density as well, but you just remember that using E equals mc squared, that you can get in between that and your energy density. And so as long as you have some sort of relationship between pressure and energy density, you can close your equations and solve these couple differential equations. And like I said before, is you just pick a central density and you integrate outwards until you hit the surface, which is the pressure goes to zero. Now, just an overview quickly of units, because I'm a high energy physicist and I think always in natural units, but not everybody thinks the same way as I do. So it's important to just kind of understand the units that I'm using here. So I use the speed of light is equal to h bar is equal to 1. But if we talk about the density of a nucleus, which is something very, very relevant for neutron stars, just to explain why, It's because a neutron star actually reaches many times the density of nucleus. And so in everyday life, we tend to think of the nucleus as pretty much the most dense thing you can think of. But a neutron star can even get well beyond that. And so that's kind of our benchmark for density inside of neutron stars. And that's 10 to the 14th grams per centimeter cubed. And so when we talk about saturation properties, I tend to think in femtometers, which is 0.16 inverse femtometer cubed. Energy density would be in MeV over femtometer cubed, same units as pressure, but in the real world, you might think of like grams per centimeter, inverse centimeter cubed, or dynes per inverse centimeter cubed. Now, in terms of how dense that is, it will be something like 10 to the 14 times denser than our sun. So it's extremely, extremely dense. So how do these things work? Going back to the pressure and the energy density, here's an example of various equations of state that exist out there. I have a lot of different types of degrees of freedom. It could be protons, it could be neutrons. I think some of these have quarks and hyperons in there. I'm not going to pick out all the different ones, but I will show you the idea of how one equation of state would then affect the mass and radius relationship. And so what I do, if I want to calculate my mass and radius, is I pick some sort of central density. Imagine I pick it right at saturation density. That's the density of a nucleus. And then what I would do is I would integrate out using the TOV equations until I hit a pressure going to 0. So this is the center of the star, and then I integrate down to a 0 pressure. And that is going to give me some point over here in one of these lines. And then next, I go up a little bit more. I pick a new central density, and then on the same line, I integrate downwards to 0 pressure, and that gives me another point here. And so you essentially keep, from a single equation of state, you keep doing that exercise, and you fill up more and more points along your mass radius curve until you see this point here where it starts to flatten off. So the idea is the following: as I increase my central energy density of the star over here, I should always have an increasing mass. If at some point my mass no longer increases, that is called the maximum mass of the neutron star. I cannot have any neutron stars beyond that mass. What it means is that that would be unstable and it would collapse into a black hole. So one of these lines here is basically saying the following: if I could measure every single neutron star in the universe, and it was basically slowly rotating or not rotating at all, magnetic fields were not enormous, and there was not dark matter inside of it. So there's a few caveats here, but those are pretty good assumptions. And so if that was the case, I would then know the mass and radius relationship of all those neutron stars. And so if I knew the mass, imagine it was one solar mass, I could look here and say, oh, this radius is the correct one. And so we then do the inverse, is we calculate many equations of state. We get a number of different mass and radius relations, and we can then exclude some of those relations based on astrophysical constraints. For instance, if the constraints say, oh, it has to be the mass of a one solar mass neutron star has to be 12 kilometers or less, then you could see we could eliminate many of these equations of state over here to the right, just as an example. So how does this work in terms of the interplay between the degrees of freedom inside the neutron star and the actual mass and radius relationship? So if I have something that I would call like a vanilla equation of state, this would be this black line here. It's just neutrons, protons, and some sort of leptons in there. That one looks like this as an example. And then I add hyperons to it. So I'm adding strange baryons. And what happens is when I add a new particle, it opens up new degrees of freedom and essentially softens the equation of state. So we can see here that as you think of your equation of state like this, like it's getting sort of stiffer and stiffer. But if you can all of a sudden open up a new degree of freedom, it just relaxes a little bit and can compress itself more into a tighter space. And so the pressure goes down. And so what happens then to the mass radius relationship is the following, is that here they're identical. You can see this is this part of the equation of state. And once you've opened up these new degrees of freedom, you soften your equation of state, there's less pressure. So there's less pressure pushing your star outwards. And so that force of gravity brings it in more and it's smaller. And that's exactly what we're seeing here, is that with less pressure, we have a smaller maximum mass. Whereas for this one, which is a stiffer or harder equation of state, then it has a heavier maximum mass because it just has more pressure pushing it outwards. So to give you an idea though, from the pressure versus energy density, if we go back, for instance, a couple of slides, it's very, very hard to see the differences, like what the degrees of freedom, what are the key points, what's interesting there. And so in fact, what can be much more useful is instead of looking at pressure versus energy density, is we actually just take the derivative of this, known as the speed of sound squared. So we just take dp to e. And here's an example of what different equations of state look like over here on the left, if all of a sudden I took the speed of sound squared and compared them. And why is this interesting? Well, you could get something like a big bump in the speed of sound that goes to the causal limit. So this is the speed of light up here. It could go even past the conformal limit, which is another thing that's quite interesting. And this is helping us to actually look for different degrees of freedom. Generally, when something happens in your speed of sound, any sort of softening or stiffening of your equation state shows up very quickly in the speed of sound and often becomes obvious in terms of what's happening. And so because of this, we often will compare speed to sound instead of looking at the pressure and energy, just because we can look for very specific features in the speed of sound and understand better what's happening with the equation state. So I showed you just as an example of a speed of sound that went up to the speed of light. And so for us on Earth, those are very, very different things. The speed of light is extremely fast. It's we get example of lightning. And if we compare that to the speed of sound, it's many orders of magnitude slower in Earth's atmosphere than the speed of light. And so the question that we could then ask is, what about this very extreme environment where the speed of light is essentially equal to the speed of sound? And so why would we even think that that's the case? Well, we can do this phenomenologically. In fact, when people were first starting to learn about neutron stars, they always assumed they were relatively light. They thought that maybe the max mass was like 1.7 solar masses, 1.8. And then new data came in. More observations of neutron stars were discovered, and they found neutron stars that were definitely 2 solar masses. And so this really made the community question their understanding. And in fact, one thing that came out of this is that you need essentially a very stiff equation of state to get up to 2 solar masses. And the solution to that could be a very large bump in the speed of sound. And so they had a number of works that were more phenomenologically driven in order to get up to 2 solar masses. There, of course, can also be theoretical motivation for why you need to have such a heavy neutron star. And so one good example of this is quark ionic matter. And so this is essentially a crossover phase transition. At low densities, you have neutrons and protons and electrons, and this bump in the speed of sound that gets close to the causal limit is actually coming from the change of the degrees of freedom from baryons into quarks on the right-hand side here. And this is the quark phase. And so it's a crossover phase transition. So that means that you're only very slowly changing your degrees of freedom from one of the other across a range of baryon densities. So to give you an example of what a lot of different equation of state could give you is we had a work where we compiled many different ones that were from various microphysical models and just plotted them to see what they could potentially look like. And so this is the speed of sound versus the baryon density in terms of saturation. And you can see here that you get quite a few different features. So this green one I want to point out is SLI, which is what one could think of as a vanilla equation of state. It has neutrons, protons, and electrons. It does not have hyperons, nor does it have quarks inside. You can get things with first order phase transitions. This is this orange dot dashed one here. That looks quite dramatic. You can get these little peaks that look almost like waves. That's typically coming from different particles, different baryons switching on. So it could be the delta baryon, or it could be strange baryons, for instance, the lambda or the sigma or cascades. It's not clear which is turning on. It depends, in that model and what its interactions are, but you're definitely getting a new particle turning on when you get these little peaks. And so this helps us to then understand better what to look for in data using these microphysical models. And so how do we check for these features systematically? We don't necessarily want to assume one specific model. We want to see what the data can actually tell us. And also the other kind of challenge here is that if we're looking in the data, it's of course easier if we did something simple like a Taylor series. But if we go back to that previous plot, it's very clear that we have these very sharp features in the equation of state. And that will be hard to capture with something like a Taylor series or even Gaussians. So we need to kind of think beyond that. Like, how could we build in sharp features to the equation state to actually search for them correctly? And so how do we do this? Well, the nice thing is the speed of sound in a neutron star, the equation state, is a one-dimensional function. It's just the speed of sound versus the baryon density, if we're assuming a neutron star in equilibrium. The other thing is that you're bounded both by stability, so the speed of sound should be real, and you should also have causality, so it should be at the speed of light or less. And so from very, very low densities, we have a very good understanding of the equation of state. This also relates to what happens in white dwarfs, and is pretty straightforward. And so this is relatively well known. Now, if you get up to slightly higher densities, you can use chiral effective field theory. This also has a pretty small error bar on it these days, maybe on the order of magnitude of like 10%. And so we start getting a little bit of a band, but not too much. And so this low density regime, we feel pretty well that we understand what's going on there. But what happens beyond that point? And so then it's a whole free for all. You know, everybody might have their favorite model, but we don't actually know what happens after the regime of chiral effective field theory. And so what we'd like to do is, in fact, build in a bunch of different types of equations of state onto here, and then run a Bayesian analysis using astrophysical constraints to actually check which of these equations of state are correct. And so then if we use known astrophysical constraints today, here are some examples of what they are. We have 2 points from NICER, this one up here and this one up here. They're coming from 2 different collaborations, which is why there's not 100% overlap from that. Now, I will say there was an April APS meeting not that long ago. There's some very small differences on this heavier pulsar. The error bars are slightly smaller. However, when they've ran their analysis, it doesn't appear to be enough to really affect any of the interpretations of the equation of state. So we don't have it in our analysis now, but it, you know, down the road, the longer they're looking at the star from NICER, the better statistics they'll have and the smaller the error bars will be. There is actually another pulsar from NICER. There's only one group that's analyzed it yet. So until both groups have analyzed it, we're kind of holding off and waiting to get that information to include that into our models as well. And then there's a bit of a caveat here. I talked about this last week. This information is extracted from LIGO, Virgo, and Kagra from GW 170817. And so this is a bit model dependent in terms of how that actually maps onto the mass radius relationship, but it is very useful to also constrain the equation state. And essentially what you do is you use something called the tidal deformability instead, but this at least gives you an idea in terms of the mass radius, like what are the constraints today and kind of how they fit into the phase diagram. So you could imagine fitting within these constraints, you could take and draw a line at 12 kilometers and pretty much just draw it up straight through the data as an example, or it could go to the left or the right. I mean, you still have some freedom, but it should fit into this overlapping regime here and somewhere up in this upper band here. Good. So now what are the features specifically that we're interested in? You could have a spike up or a smoother sort of bump up. These would be things like a crossover phase transition, like I said, from like quark-ionic matter or something like this. You could also have a spike downwards. This could be from a critical point. If it's at 0 temperature, it's actually a quantum critical point, which would be quite interesting to find as well. And then you could have a first order phase transition. And so that if you're in equilibrium, you have this long plateau in your speed of sound across some range of baryon densities. And so these are actually specific features that we can build into our model and check for them. So how do we do this? Well, what we want to do is we want to do a multi-scale approach. You want something that has like a long correlation length. And they can kind of get the overall picture of the equation of state. But then you want to build in these sharp features as well. And so this is what we do here. We use Gaussian processes, which are a way to model functional forms. It's nice because you can easily sample in a way that ensures that it's causal and stable. And then you have some sort of correlation functions that you can build in, which is essentially telling you the length of your correlations across baryon density in your system. And so what we do in our approach is we take both the Gaussian processes to get the long correlation lengths, and then we build these specific features on top to look for like a spike or a bump or a plateau to understand better what's happening with our equation of state. And so this is an example of what that looks like. These are the Gaussian processes without building these features. The gray ones are our benchmarks, and that's compared to some of those example microphysical models from before. So you can see that the long correlation lengths are certainly not compatible with the microphysical models, and we need to still build in those features. Now, here on the right, we can see with structure. And so this is an example of different features that we have built into the equation of state. And so what happens here is the dark lines are up to the max central density of the neutron star, and anything that's a light color is beyond that regime. It would already be a black hole, so we can effectively ignore that. So that gives you an idea of also what the max central density of a neutron star would look like. It's around 4 to 6 times saturation density if we take our current astrophysical constraints. Good. So then how do we do a Bayesian analysis? Is what we can do is we can take, 2 different equations of state, for instance, and then we compare them both to astrophysical constraints and as well to nuclear experimental constraints and specifically saturation properties, that those we know pretty well. And so you can apply all of these into a Bayesian approach, and the outcome is a likelihood. And so what do we actually find today with these results? Well, so if we look at our approach where we had the building and the structure into the speed of sound, this is what our prior looks like. Essentially, we did originally have other things in the prior, but we have to put in certain cuts that it has like at least a certain maximum mass in order to fit and actually compare to some of that data there, because we have this very heavy pulsar as well. And so that's why your speed of sound generally is already going up in this direction because of these constraints. However, once we apply all the constraints like saturation property, the radius constraints, everything, we do see that the one feature that we can really see is a very clear trend that it must go pretty sharply up to around 2 times saturation density. Beyond that, it's very unclear what needs to happen, because remember, this is just a posterior band up. So basically 68% and 90% from this range. But what happens inside the band is unclear. You could go like up and down. You could have a plateau. You could do a lot of different things. And so anything that's black has a non-zero probability that you could actually hit that part in the space of CS squared versus NB. But we do know, at least at low densities, that we should see the sharp increasing trend. So what other kind of constraints could actually happen with a neutron star? Well, the interesting thing is that we measure this thing, GW190814, this mystery object, and we do not know if it's a black hole or a neutron star. It could be either one. So it was some mystery object merging with a very, very large black hole. And the mass of this was in something called the mass gap. It's 2.5 to 2.67 solar masses. And what that means is it's a bit heavier than we expected a neutron star to be, but it's also a bit lighter than we expect the lightest black hole to be. And so it's really a regime that we have a hard time understanding, and we're still trying to figure out this physics. So why is this interesting? Well, it turns out that if you look at your speed of sound, a large bump in the speed of sound can actually get you very, very heavy neutron stars. And so here's an example of different bumps. These are drawn by hand, just made, and we can put the bump at different locations and see exactly how that would affect our mass radius curve. And so if we have a very late bump that's happening at large baryon densities, we see that it doesn't produce a very large maximum mass. But then if we have something that happens very, very early at low baryon densities, we can produce an enormous maximum mass, in fact. And if we get something here kind of intermediate, around 2 times saturation density to like 3 times saturation density, we get something that's right on the money for GW190814. So that's interesting, and that's something that we can look for in the data. Now, unfortunately, with GW190814, we did not have enough signals from gravitational wave detectors to actually distinguish if it's a neutron star or a black hole. But we could look for this. There's other things. We might have another merger that's in this mass gap. We might have other astrophysical objects that we find in this mass range. And so this is something to think about for the future. Now, if you were to take a bunch of different equations of state that reach up to 2.5 solar masses at the very minimum, you can see that the one feature that you get sort of uniquely here is a very, very steep rise in your speed of sound. And that seems to be a clear feature no matter what. It might happen at different locations, but it definitely is there in order to produce 2.5 solar masses. So what's the big caveat here? Well, when this came out, there was one group that said, wait a minute, you cannot have this because it would be inconsistent with heavy ion data. And so they used data from back in 2002 to say, this is a constraint, and anything that has a lot of pressure, enough pressure to produce these very, very heavy neutron stars would be ruled out. But we need to be cautious here. So heavy ion data, I have this danger Will Robinson here. This is not actually data. What this is, it's not even a Bayesian analysis, this band here. This is based on a very nice 2002 paper, but it was essentially taking a specific model, varying it a few times, and then producing a band from that. But it was never even really fitting the data or anything along those lines. So it's more of a motivation for future work rather than something you could say that is a constraint by any means. So how could you actually use heavy ion collisions to constrain these things? Well, the interesting thing is you have essentially two ions that you boost to the speed of light and you collide. And so that's this A and B here, and you have your collision. And then you essentially have two different possibilities. On the left side, you could have a case where you don't produce a quark gluon plasma. So essentially you have some sort of hadron formation, you have interactions. At some point, you stop interacting and you hit the detector, and that's where you get all your information. On the right-hand side, which we know is definitely happening at high energies, is that you're reaching really, really high temperatures. And so it's an analog of what happens at large baryon densities, and you unlock quark and gluon degrees of freedom. And so you reach this new phase of matter called the quark gluon plasma. And at high energies, you also have a crossover phase transition into hadrons. Those hadrons are then interacting with each other until they eventually cool out, expand, freeze, and then they hit the detector. And so these are the kind of different scenarios. So the reason I point this out is that if at very low beam energies, so they don't have a very high temperature when they hit each other, there is a chance that you can go from a quark gluon plasma phase until you're just having hadron resonance gas. And so this is an open question, exactly how high of energies do you need to produce a quark gluon plasma? And so to give you an idea why this is relevant is that this is our phase diagram for quantum chromodynamics. We have temperatures up here, we have chemical potentials down here, or you could also think of this as baryon densities, either way. The idea is that at very, very high energies, everything is heavily Lorentz contracted. They're hitting each other with such high energies that you easily produce enough temperature up here to create the quark gluon plasma that eventually expands and cools over time and then crosses into hadrons. And this is eventually measured by the detector. Now, if you go to lower and lower beam energies, then your ions are no longer so strongly Lorentz contracted. They're actually three-dimensional. And as they pass through each other, they have enough time to capture individual baryons. Their baryons are stopped. And so what this is like in condensed matter, when you start doping your material, you're doping this with baryons. And so you're making something more baryon rich, which is getting you closer to the neutron star territory. But then the quarter caveat here is that also that lowers the temperature. And so at some point you might be under the regime where you no longer have a quark gluon plasma. It might just be hadronic interactions. We don't actually know. Now, to give you a picture of what this looks like, I can compare it to a neutron star merger. Here is still in spiral phase when they're just about to touch. The two neutron stars are already deformed. Then they start spinning around each other. You can see here. And eventually it looks very spherical at the end at long time scales. And to give you an idea, these time scales are on the millisecond scale. If we compare this to heavy ion collisions, we have two ions. They're slightly Lorentz contracted when they collide with each other. They then hit. They start kind of rotating a little bit, but you have a clear elliptical shape that's still coming out of this thing. And so the point is that this is a much, much, much shorter time scale. This is femtometers, so 10 to the minus 15 meters. So very, very tiny time scales that we're dealing with up here or down here in comparisons. And we still have structure in these things. In fact, this structure, this elliptical shape, is something that we measure in the data. In fact, we measure something called V1, which is the direction it's flowing, and V2, which is the elliptical shape. And that's what we actually use to try and extract information about the equation of state in these very low beam energies. Now, there are other key differences between heavy ion collisions and neutron stars. One of those is strangeness. Heavy ion collisions actually impose strangeness neutrality. That does not mean that there's no strange particles. In fact, there's a lot of them. It's just that they're conserved. And so whenever you produce strangeness, it's always in a net pair. It's like strange quark and anti-strange quark. Whereas in neutron star mergers, it's not the same case. You actually can have weak decays because of much longer time scales. And so strangeness is not most likely in chemical equilibrium. Instead, you can get a net amount of strangeness because of this. The other key difference is that we have very different charge fractions. So in heavy ion collisions, you have many, many protons. And so you have a finite amount of charge. In fact, you have quite a bit of charge. Whereas for neutron stars, they're old, they've been sitting there a long time, they're completely electrically neutral, otherwise they would not be stable. The other key difference, especially if we're talking about a cold neutron star that's isolated, it's in equilibrium, it's zero temperature, whereas heavy ions can be very, very far from equilibrium, and they're definitely at finite temperature. So, but how can we then do comparisons between them? Well, the most important feature is really understanding how the charge fraction is changing as we go from heavy ions to neutron stars. And so this can be seen here in the bottom right, is that heavy ion collisions are essentially symmetric nuclear matter, where you have an equal number of protons to neutrons, whereas neutron stars are asymmetric matter, where you might have about 10% of protons or even less than that. And so you need to find some way to switch your charge fraction, your ratio of charged particles to total number of baryons in your system. Now, there was a recent study that did this completely independently of neutron stars. They just did a Bayesian analysis in heavy ion collisions compared to data. And in this case, they did actually build in structure in their speed of sound. And when they did that, they get this sort of interesting, very interesting pressure where it seems to spike upwards. And so this might very well lead to a speed of sound that has a sharp peak into it. And so the question is, if you have something like this, could we relate this to neutron stars? And how would that affect things going both from the question of heavy ions to neutron stars and neutron stars to heavy ions? So we could then imagine the following scenario. Imagine that the gravitational wave people and also NICER have done an extremely good job. And we can then know perfectly what the neutron star equation of state is. It's essentially a line in pressure versus energy density, and we know the corresponding speed of sound. How do we actually connect that to heavy ion collisions? Like, how could we do comparisons on both ends? Can we constrain the equation of state? And what happens actually to these features? Like, if I have a big bump in the speed of sound for neutron stars, once I change my charge fraction, would that still appear in heavy ions? And so the way that you can actually do this, you define this quantity YQ, which is your charge fraction, your ratio of electric charge to total baryon number. And then you can define then this isospin asymmetry quantity, where it's essentially 0 for symmetric nuclear matter, or it's larger than 0 for asymmetric nuclear matter. And then you take your energy and you just expand around delta. So this is called the symmetry energy expansion, where you start with symmetric nuclear matter and you work outwards in terms of delta till you get to the point. You can do a bit of math. I'm not going to go through that here, where you can actually connect your energy density from neutron stars to your energy density from heavy ions. Now, what does this actually depend on are then these 4 quantities here. This comes about because you don't just expand in the direction of YQ, but you also are expanding around saturation density. And so these are properties that you can get from low energy nuclear physics experiments. At least these first two have been measured, and these second 2 you can get motivation from a variety of theoretical approaches. But you still have 4 knowns, and at least even these guys have error bars on them. And so if you give in equation of state from neutron stars here, you could get out a heavy ion equation of state, although you would have to sample over all 4 unknowns in order to do that. So we did exactly that. is we said, okay, imagine that this is my neutron star equation of state, this black line here. I'm just guessing something, but I want to see what it looks like. And then I expand across all of these four unknowns using reasonable values. When we have experimental constraints, we apply those. When we don't, we use our best knowledge of theoretical constraints, and we get a bunch of lines here, which are these expanded equations of state. And so essentially what you see is that the bump occurs exactly at the same location, which is really encouraging. So the location of the bump is something that isn't going to change as we change our charge fraction. That being said, it's clear that the magnitude of the bump can be sensitive to what these coefficients are. Now, the other thing you can also see here is that we definitely have equations of state that reach points beyond the speed of light. So those are acausal, and ones that would end up being unstable. And so what we actually do is cut off those equations of state. We remove any unstable or acausal solutions. And so what we do is we get then this posterior for our speed of sound that would be used for heavy ion collisions. And the other interesting feature is then we can get some corner plot that is interesting, especially for low energy nuclear physicists, on constraints on these four coefficients, on the symmetry energy, the slope of the symmetry energy, and these other two, just based on causality and stability. So doing that, we then talked to our hadron transport friend Agnieszka, who then was able to run these in simulations to compare directly to heavy ion data. And so what you see here is this is compared to both directed flow and elliptical flow. And we didn't do a full Bayesian analysis because this is very, very time consuming simulations. It takes often a week to produce one data point in this plot. And so instead what we did is we picked a few locations of a big bump in the speed of sound, because we wanted to see, could we actually produce a very heavy neutron star that was like 2.5 solar masses? And so all of these equations I state here can essentially produce very, very heavy neutron stars. And so what we found is that indeed, if we have a peak in the speed of sound around 2 times saturation density, that's here, this one in blue, this produces a neutron star that's just below 2.5 solar masses, so it's essentially there. We can indeed fit the data, which is quite exciting. So it doesn't seem like heavy ion collisions are eliminating this possibility at all. In fact, it seems like equations of state that produce very heavy neutron stars are compatible with the data, although this definitely takes more exploration down the road. So what do we actually need to do? The first thing is we need to take a bunch of different equations of state and actually convert over to heavy ions. Now, the main bottleneck here is then running the heavy ion simulations, these hadron transport codes, because they take so long to run. The other kind of challenge is on that side, the code also needs some upgrades. They need to include momentum dependent potentials and some numerics improvement in order to speed it up. But in the future, I think this is definitely possible and something we have to look forward to. And also the other thing that can help in the meantime is, of course, better constraints in the symmetry energy coefficients, the charge density with a neutron star, and of course, more data from NICER and gravitational waves. In fact, I believe last week there was already a mention of a potential neutron star black hole merger from the latest LIGO Run 4. So there might be new data coming out soon. Now, I'm getting to the end of my talk, and I will say, just kind of flash some other recent work that my group has done that I'm quite excited about. And so this is the idea that once you have the post merger, so mostly what I've been talking about here are neutron stars that are isolated or in the inspiral, they haven't actually touched each other. But what happens when you have finite temperature in a neutron star? And so we had this idea of well, imagine we knew the zero temperature equation of state, how could we then go to finite temperature? And it turns out that we can take a note from what is done already in heavy ion collisions with lattice QCD. In that regime, you're at 0 baryon densities, and lattice QCD can only be calculated at finite temperature and 0 densities. And so what they do is they then perturb around this and they expand in the chemical potential over the temperature. Now, the issue with that is that that is not a great expansion, because essentially you need to go to such large chemical potentials and your temperature is actually pretty low. So you're talking about expansion where your order parameters on the order of 3 or 4 or something like this. So then we had the idea, why don't we inverse this? Why don't we take something where we're expanding from 0 temperature upwards and comparing T over mu B? And so the chemical potentials in the range for a neutron star is well over 1,000. And the temperatures that are relevant are on the order of 100. So if we think about an expansion, it's on the order of 0.1 or even less than that, which is really pretty good for a Taylor series. So then we actually did this expansion for the pressure. And what's really nice here is the first term is just the pressure at zero temperature that we can get from neutron stars that are cold. The second term is the entropy, but in the limit of zero temperature, which we don't know of any microphysical model that has finite entropy at zero temperature. So we can actually eliminate that term. For the most part, that's normally zero, unless you have really, really extreme weird systems that could have a finite entropy at zero temperature. And then basically you start with your T squared term. And this is your heat capacity. And so you just need this at the zero temperature limit. And so we then wanted to check what this looked like using a proof of principle approach. And so we took a relativistic mean field model. You can see a zero temperature equation of state here. We calculated the heat capacity and we use this expansion. And here is the truth, is the red line here. And you can see our expansion is essentially right on top of this for the order of T squared. There's some very, very tiny deviation at low chemical potentials, but we have some ideas of how to fix that. And so the idea is that you can get this essentially a percent level prediction at 100 MeV just using this very simple Taylor series to do the expansion. And it looks so far, at least, like the third order term is not really playing much of a role. So it's easy to just cut it off at T squared. So this is something pretty exciting once we start getting post-merger data from gravitational waves in the future. One other brief advertisement is for the Muses collaboration. This is something that I'm in leadership for. And this couples together nuclear physicists, particle physicists, computer scientists, gravity physicists, astrophysicists. And essentially what we want to do is take a lot of these equation of state codes that are microphysical. Oftentimes they're proprietary, they're written in outdated language. And we want to make them all open source, and we want to help to essentially bridge the gap so that people that are new to equations of state can then use an open source equation of state that's well documented, easy to use, and start doing some of these comparisons. So we're going to have the ability to run the mass radius relationship, tidal deformabilities. You're going to be able to do certain things for heavy ions as well too, and make direct comparisons to data. So this is quite exciting. It's an ongoing collaboration. We should have the alpha release actually out in about May. And so some of my PhD students are working on this as well. So that brings me to my summary. I hope I convince you that the maximum mass of a neutron star is interesting. And it is possible to reach a quite heavy one if we have some sort of dramatic change in the degrees of freedom. For instance, if we had quarks in a star, or the speed of sound that's going to the causal limit. Heavy ion collisions can be used quite usefully to help constrain the speed of sound. And so now we really need to have much more talk between these communities in order to do so. And then from the current data, we have some hints that we could have this bump in the speed of sound, but we really need better statistics and we need more data. And so hopefully we'll have that in the near future. So thank you.
Thank you very much for a very lively and very interesting talk. Do we have any questions?
Yeah.
Who's first?
Sure. So when you're talking about bumps in the equation of state, you're saying how those then relate to, you have new degrees of freedom switching on, or you might have a new type of baryon being introduced. Is the height of the bump related to the parameters of that new degree of freedom? Like, can you rule out? So, well, what inspired it is when you showed your likelihood plot, where you had large bands that then sort of constrained where your equation of state could go. Are there then constraints on how big the bumps could be that indicate degrees of freedom based on your likelihood constraints?
Yeah, that's a good question. So first of all, just to kind of answer about like what different sizes of the bumps would mean. So generally, the quark degrees of freedom, like a change into quarks, produce a much larger bump. It's a much more dramatic phase transition. Whereas if you have these smaller bumps, that's generally things like a new particle, like a delta baryon or strange baryon or something. It's a bit hard to distinguish between those different types of particles, just because if you change their interactions, it might shift which one comes first in baryon density. So that's a bit more degenerate. Now, in terms of if I go back to my posterior, like, is there ways to eliminate one or the other from the data? Right now, it's really tough because if I go back, let's see if I can get back to that plot. Oh, here it is. You can see here that I can really say that there's an increase around saturation density and maybe up to 2 times saturation density. But beyond that point, it's really hard to see. So basically, when you see a darker color, that means an equation of state passes through that point, but it's not telling you how it's passing through that point. It might pass like this or like this or like that. And so when it kind of spreads out like this means that the equation of state could do many different things. And so we don't actually know what's the right answer at this point.
Okay.
I do think that like heavy, just one other comment, heavy neutron stars will tell you much more about these large densities. So if we get better data, especially with the radius of heavy neutron stars, that will be very constraining.
I have one sort of complete shot in the dark question, which when you actually have the equation of state for neutron stars, or specifically when you're talking about the speed of sound squared, you could use the position of the bump to get to higher masses in the neutron stars. You could have a radius versus mass. And then when you compare that to heavy ion collisions, you could see the same sort of bump. Is there any relationship that's, I want to say, the same in terms of some sort of mass? Or is that purely just the gravity of the neutron star that you're then talking about?
Yeah, no, exactly. So if you go, if I go back a little bit, the location of the bump is definitely telling you about what the maximum mass of a neutron star would be. Oh, no, sorry, I went the wrong direction. Was it? It was later on. It was this guy, right? And so on this end, exactly. So if you put the bump at a lower baryon density, you get a heavier neutron star. And so that's like this blue line is related to this one here. And then if you add in the heavy ion constraints, so this is this brown guy here. Heavy ion constraints are most consistent with this specific equation of state, where you have the bump around 2 to 3 times saturation density. And the interesting part is that does relate to essentially this maximum around here that's consistent with GW 190817. Now, the kind of caveat before we get too excited and say this is a neutron star or not, is that, I mean, if you start playing with the overall magnitude of the bump, like if I brought it down a little bit or up a little bit, you know, that could make me fall out of it. Like I could be a little bit too low, could be a little bit too hot, you know, stuff like this. So we don't have enough constraints. We could say from heavy ions, it looks like more or less 2 to 3 times saturation density, but you know, all of the finer details, I think we're actually waiting on a lot of new data from heavy ions. And so that's something that I suspect in the years to come, we'll have a much stronger answer on the heavy ion side.
Okay. All right, thank you.
You're welcome.
More questions? So in from the heavy ions, what kind of data are we looking at when you use it from heavy ions? Is it beam energy scan stuff or?
Yeah, exactly. So I didn't really talk too much about it in detail, but it's a good question. It's essentially it's the fixed target regime that is by far the most important. So that was when, for those that aren't familiar, essentially normally you run heavy ion collisions in the collider at the relativistic heavy ion collider. And so they you know are accelerated around this ring and they collide with each other. Now, what happened with the fixed target is in the beam energy scan, they put a tiny gold foil within one of the colliders and it hit that. So it was a fixed target experiment and that allows you to go to lower beam energies. And so this was in this regime here. And so we have, I think, only 2 data points from the fixed target as of today, but they've ran many more. I don't know. I know they've ran 7.7 and I know they've ran a pretty good scan of this, but I don't know exactly what beam energies ran at the end because that's something that changed over time. Now, the ones that they have available today, I can go back to this plot. You can see that I only have 2 data points from STAR, and I have 1 data point for HOTTIES. There is actually old data that's not shown in this plot from like SPS. The reason I don't show that is it's actually inconsistent with the STAR data. And so there is some, caveats here that some of this older data doesn't seem to be quite compatible with the newer data. Now, of course, the detectors have improved enormously and everything. So it could be just better detectors, but it's a bit hard to say.
Okay, then one more question. Thank you for that. One more question about I guess it might be a few slides before this. There was this plot showed by a recent paper, the one by Dima.
By Dima? Okay, yes.
Yeah.
This one, yeah.
Yeah. So yeah. Do you mind just maybe explaining what it is that was? I'm sorry because this is someone else's work. But what it is that was done over here actually?
Right. So what they did in that paper is they did a Bayesian analysis by basically making the speed of sound a step function. So it was like they had different steps in the bearing density. And it was like when they put a big peak at one point and then came back down. And so then that's why it kind of looks a little choppy here. It looks because it was essentially steps in the speed of sound that then they integrate over to get the pressure versus the bearing density here. And then they did a Bayesian analysis exactly comparing to this data here, the hotties and the star data, and using that as constraints in their model. And so then, but there was no connection to neutron stars, right? So they didn't make that connection to what the neutron star equation state would look like. It was just done completely self-consistently within heavy ions.
So okay. So I see this kind of center of mass energy, those root S's are pretty small. So you got in the order of what, 4.5 to 7 G.
Yeah, this one. Yeah, it's very, very small beam energy. So that's why you using a hadron transport code is the idea is that it's such low beam energies that you don't produce high enough temperatures to probably have much of any influence from the quark gluon plasma phase.
So would you have any use for I don't know, say something like higher, but still say you're still looking at high bearing density, right? Like the fragmentation regions of this collision. Would that be of any use in this whole matching of equations of states that you were doing?
Yeah, I mean, the higher beam energies are very useful. The reason that we didn't explore those was kind of two reasons. One, they don't have the data out yet from the beam energy scan. So we didn't know if we should trust the older SPS data there, because of this issue with the mismatch. The second reason is that if you get to higher beam energies, at some point, the quark gluon plasma is going to matter much more. And so in fact, what you'd probably want to run is something that is a combination of hydrodynamics with a hadron transport code. Now that exists, but one would have to redo the whole Bayesian analysis approach with that as well. And so there's been various papers on what beam energy that's most relevant. Some people say 7.7. I believe Hannah Elfner's group actually ran something around 4 GeV and found it looks sort of hydro-like as well, or at least some contributions from hydro. So it's an open question at what point can you just do hadron transport versus at what point would you need something else in there?
But just to make sure that I'm getting this right, on these plots, your peak in the speed of sound is in a range where hadrons are the dominant degrees of freedom.
Yeah. So it's a kind of funny model because essentially this is Agnieszka's PhD thesis that she did, where she puts in these potentials. So you get phase transitions in her model. It's just that it's some sort of weird hadronic phase afterwards. Now you could think of it as like a quark phase, but they don't have those, have to explicitly build those degrees of freedom into the hadron transport model, which I don't know anybody who's done that yet. It would be interesting to look into.
Okay, so in relation to this QCD phase transition, yeah, okay. Out there at high densities, this is a really funny thing, but because we essentially know nothing quantitative. are there any constraints from anywhere where to put the phase transition line? I mean, with whatever error bar on it.
Mhm. Yeah, that's a great question. So, I mean, we have some constraints. You can get PQCD constraints that are 40 times saturation density, but by the time you actually extrapolate that to the central densities, which are, you know, what you'd actually have constraints, it might eliminate like less than 1% of your equation of the state. It's a very, very small effect.
I mean, yeah, coming perturbatively from extreme mu B is extrapolating down. I mean, you lose probably all hope of being exactly
Yeah.
anywhere.
Yeah, exactly. Now one thing I will say is if you have a first order phase transition, you would produce something called mass twins. And so that's where you have one stable branch and a second stable branch. And that is something that maybe not today we have such good constraints, but if you keep measuring more and more neutron stars and you don't see something with a second stable branch, then it seems pretty convincing that at least the phase transition would not be in the range of baryon densities of the neutron star itself. It could be right afterwards. So you can actually have like a big phase transition that only produces one stable branch and everything else is unstable. But that would be a bit disappointing because you'd want to have it like within the neutron star so you can actually measure it.
Okay, thanks for that reminder about the two stable options. That's something I shouldn't forget about, because that was one of the things that I learned last time in your last talk. And that's a really distinctive kind of.
Yeah. Yeah, I didn't talk about too much here just because, you know, there's not data on it right now. There is actually the second, I sort of briefly mentioned NICER has this third pulsar. And so one of the groups came out with data on that, and it is a little bit to the left. It's at lower radii. So it makes you a little bit hopeful. But the other group has said that they don't trust the results yet and hasn't produced results. So until that happens, I'm, you know, just being patient, trying not to. Yeah.
Absolutely. Very good. Do we have other questions?
It might be a bit of a trivial question. I don't even know if it's actually gonna go somewhere, but when you add something to your equation of state, for example, that creates a little bump or a little something, and you mentioned you have to integrate down to zero pressure to get the mass radius curve. But I noticed that all of the mass radius curves tend to be like a semi-nice, smooth, nice looking curve, whereas the equations of state might end up looking quite jagged. Will any sort of perturbation on this equation of state always produce a nice mass radius relation, mass radius curve, or do they also look jagged and janky?
Yeah, for the most part, they always look very, very smooth, and that's because it's a quantity that's integrated, like you said, across, basically from zero pressure to some large central density. The only exception is exactly what we were talking about a moment ago, were these mass twins. And so essentially, I can just draw it. I don't think I have it here, but I could. Let's see, do a whiteboard. And so let's see. Essentially, I can do something like this, where I have a mass and a radius. And if I have a second stable branch, it would look like that. It could actually, I could have one that goes above, or it could even just be like this. There's a lot of different options, but you only would have one. Well, you would have one, or you could have, sometimes there's very bizarre equations that say they have a second one, but that's very rare. Now, what can happen as well, I'll draw this over here, is a lot of this spiky structure and the speed of sound can lead to equations of state where your mass radius curve changes. You could get something that goes to the left or the right. And the one that goes to the right generally has more like the big bump in the speed of sound. And that's happening at low densities. Whereas the one that goes to the left, it might come from tinier bumps, or it has a very late bump, or just boring equation state where there's nothing in it. But if you want something that bends to the right, essentially has to have a very steep rise in the speed of sound at some point. And so it is kind of funny that you have all these jagged features in your speed of sound, and then once you get the Bass radius curve, it's very smooth. But it's just because it's something that's, you know, essentially integrated over the entire star.
Cool, thank you.
Thank you. That means that the question is run out of questions here. Well, then let's say thank you again.
You're welcome.
A lot of fun. Yeah.
All right.
So